Zoom, watch YouTube, send tweets, and browse the web. You could say they're almost as important as the world itself spinning. In fact, you're able to watch this video on YouTube because of IP addresses. Every digital device we use, whether it's a computer, laptop, phone, or tablet, gets assigned an IP address. This address enables devices to communicate and connect with each other. Think of an IP address as similar to your house address. Without it, no one would be able to find you and send you mail. Now, let's discuss public and private IP addresses. Our IP address system has a limitation. There aren't enough IP addresses to cover all devices that need to connect to the internet. The current IPv4 system has only 4.3 billion IP addresses, which isn't sufficient considering there are over 8 billion people on the planet, each with multiple devices. To address this scarcity, a system was developed to reuse a group of IP addresses within a local area network or LAN, which are not accessible over the internet. These addresses can be used repeatedly within each local network, helping conserve the limited number of IP addresses available. These private addresses typically start with numbers like 192.168.10. or 172.16. You might have noticed these private IP addresses, such as 192.168 or 10 point something when checking your network configuration, for example using ifconfig on a Kali system. These addresses are only usable within your local area network and cannot be used to communicate over the internet directly. For internet communication, your private IP address needs to be translated into a public IP address by a network address translation or NAT device. This translation process allows devices within your local network to access the internet using a shared public IP address. This is necessary because private IP addresses within a local area network cannot be directly used on the internet since they are not unique. Many LANs use the same private IP addresses internally. When a machine inside the LAN wants to communicate over the internet, it sends a request to the NAT device. The NAT device then records the internal IP address of the machine in a table and converts it to the external IP address of the router. When the response packet returns from its destination on the internet, the NAT device checks its table and forwards the packet to the internal IP address of the original machine within the LAN. This whole process happens seamlessly, and individual systems or users within the LAN typically don't realize that their private IP addresses are being translated to a public IP address by the NAT device to enable internet communication. The next protocol is DHCP. Dynamic Host Configuration Protocol, or DHCP, is a protocol that dynamically assigns IP addresses. This means that instead of having a fixed IP address all the time, your device gets a new IP address each time it connects to a network. DHCP is commonly used on local area networks or LANs where private IP addresses are used. When a device joins a LAN, it sends a request to the DHCP server asking for an IP address. The DHCP server then assigns an IP address to that device for a specific period known as a lease. This lease defines how long the device can use that particular IP address. The interesting part is that each time you connect to the LAN, you're likely to receive a different dynamic IP address, although usually within the same range. This dynamic allocation of IP addresses by DHCP helps manage and optimize the use of available IP addresses within the network. Alright, let's talk about the next protocol IP, or Internet Protocol, in an easy-to-understand way. IP is like a travel guide for data packets on the internet. It helps these packets know where to go, the destination, and where they're coming from, the source. It's often paired up with other protocols like TCP to form what's commonly known as TCP/IP. Now, let's take a peek at what's inside an IP packet header. This header is like the packet's ID card, carrying information that can be super useful for someone exploring hacking or doing forensic investigations. In the first row of this ID card, version, it tells us which version of IP is being used, either v4 or v6. Internet header length. This is all about the length of the header. Moving on to the second row. Type of service, or TOS. This part describes the packet's service type, like if it's focused on speed, reliability, or cost effectiveness. Total length. This tells us the overall size of the packet, including its data. In the third row. Identification. Each packet gets a unique ID, helpful for putting together fragmented packets. IP flags. This field helps us know if the packet is split into smaller parts or not, which can be sneaky for bypassing security measures. Fragment offset. If a packet is split, this field tells us where it starts in the sequence. Now, on to row 4 and 5. Source or destination. These are super important because they show where the packet is coming from and where it's headed. Finally, in row 6. Options. This is a flexible part of the header, and it's optional to use. Padding. If needed, this part fills in any extra space in the header. Understanding these details helps in figuring out how data travels across the internet and can even give clues about the systems sending and receiving the data. The next protocol is TCP. In the TCP header, there are several important fields that are crucial for both aspiring hackers and forensic investigators to grasp. Starting with row 1, source port, destination port. These fields are vital as they determine the source and destination ports, showing where the communication is coming from and where it's headed. Moving on to row 2, sequence number. This number is generated by the sender's TCP stack and ensures that packets are arranged in the correct order when they arrive. It's also crucial in preventing man-in-the-middle attacks. Next, in row 3, acknowledgement number. This echoes back the sequence number, confirming that the packet has been received. If no acknowledgement is received within a set time, the sender resends the packet to ensure successful delivery. This reliability distinguishes TCP from UDP, which doesn't guarantee packet delivery. Skipping ahead to the flags in row 4. SYN initiates a new connection. FIN signals the normal closing of a connection. AC acknowledges receipt of a packet, crucial after the three-way handshake. RST indicates a hard close of a connection, often used to communicate errors. ERG marks urgent data in the packet. PSH directs the data past the buffer to the application. Understanding these flags is essential, especially for those familiar with recon tools like Nmap or HPing3, as they're used to create packets for specific purposes, such as evading detection or eliciting responses from secure systems. In row 4, the window size field manages packet buffering, aiding in flow control. It's also useful for OS identification, as different operating systems have varying window sizes, allowing for OS prediction with about 80% accuracy. The checksum in row 5 ensures data integrity, while the ERG pointer indicates urgent data if the ERG flag is set. Lastly, row 6 contains options and padding, allowing for additional information and aligning the TCP header to a multiple of 32 bits. Understanding these TCP header fields is crucial for analyzing network traffic, identifying potential security threats, and gaining insights into the systems communicating over the network. Every TCP connection starts with a three-way handshake. Imagine you're trying to start a conversation with someone, let's say ordering a pizza over the phone. You dial the pizza place and say, "Hey, I'd like to order a pizza." This is like the SYN packet where you're initiating the connection and saying, "Hello, I want to talk to you." The pizza place responds, "Sure, we're ready to take your order." This is like the SYN AC packet where the server acknowledges your request and says, "Hi, I'm here and ready to chat. Let's get started." You then confirm, "Great, I'd like a large pepperoni pizza, please." This is like the AC packet where you acknowledge the server's response, confirming that you're ready to proceed with the conversation, or in this case, the pizza order. After this three-way handshake, the pizza place knows you're ready to place your order. Just like in TCP, both the client and server know they're ready to start exchanging data. It's a way of ensuring a smooth and reliable connection before diving into the main conversation or data transfer. Let's dive into UDP or User Datagram Protocol. UDP is a different kind of beast compared to TCP. While TCP is all about establishing a solid connection like a handshake and ensuring every piece of data gets delivered, UDP takes a more carefree approach. It's like the difference between sending a formal letter with tracking TCP versus tossing a postcard in the mail UDP. Here's what makes UDP unique. Unlike TCP, which requires a formal connection setup like the three-way handshake we talked about earlier, UDP doesn't bother with all that. It just sends packets out into the world without worrying about getting a confirmation of delivery. Because UDP skips the whole connection assurance process, it's lighter and faster than TCP. This makes it perfect for applications where speed matters more than ensuring every single packet gets through perfectly. UDP shines in scenarios where efficiency is key and losing an occasional packet isn't a big deal. Think of streaming music or video missing a few seconds here or there won't ruin your experience, but lagging behind because of a slow connection would definitely be a problem. Some of the key protocols that use UDP include DNS, SNMP, or NTP. We'll dive deeper into these protocols later on. Now let's talk about the next protocol, ARP, or Address Resolution Protocol. ARP is like a translator for devices on an Ethernet network. Its job is to match up IP addresses which are logical with MAC addresses which are physical. This way, when a new device joins the network, ARP assigns it an IP address within the network's range and links it to its unique MAC address. This information is crucial for network devices like routers, gateways, and switches to correctly route traffic to the intended destination. Now, here's how a RP works in simple terms. Imagine you have two computers on the same Ethernet network. Let's